Susan, can you see my screen?
Yes, I can.
Okay.
I can see your screen.
Thank you. So, first of all, we'll talk about DASCA model and Bayesian networks. So, in today's objective essay, we can explain the types and application of DASCA models, describe Bayesian statistics, identify characteristics of Bayesian networks, describe probabilistic influence in Bayesian networks, describe purpose of Bayesian methods, identify the applications of Bayesian network. So we have like 6 of them here. So introduction to DASCA models. Now, to specify dependencies in a domain under study, the conditional distribution functions that represent the quantitative information about the domain need to be estimated. So this approach is tiresome or time-consuming. For example, large domains like retail, you have 100 variables, 1,000 variables. So let's look at this instance, for example, now a guy that is with us. So let's even look at the guy. So let's say we have the head, we have the shoulder, we have the elbow, blah blah blah. So you want to like identify the kind of positioning of this person now. So the position of the head, for example, is the position. Let's say position of the neck now. So the position of the neck is dependent on the position of the head, while the position of the shoulder can say be dependent on the position of the neck, and so all those dependencies. Stuff like that. So the solution is to create a graphical model which defines a class of probability distributions over a set of random variables using a graph. So, given an image x in x, how precisely the human pose can be estimated in the image y in y. So the position, as I said earlier, the position of the head or neck is dependent on where the head is. Then it follows in a particular order, like trying to find dependencies. The context starts with the estimation of different body parts, as you can see on the screen here. Then the formula to calculate body parts, for example, estimating head, you have y of head, and the likes of that. So all these ones are just like mathematical jargons, anyways. We don't need to bother ourselves about this. So with this classifier, a score is evaluated and recorded for all positions in the picture for all body parts captured. So this process is repeated for all the body parts until the entire image has been scanned for different body classifiers, as shown in the figure in the following slide. So we have this guy to be a function of different body parts. You have the head, torso, and the likes of that. So this probability are being calculated, and we'll be able to find dependencies using the graphical model. So a probability distribution is used to capture uncertainty of a phenomenon, given some data. Formally, it is represented as this: P of a particular y in y. So y is can be is a random variable. So for any y in y, there is a P of y, which is the probability of y, which is actually greater or equal to 0, because probability is actually greater or equal to 0. Now, if you calculate the sum over the set of points, so all these body parts, so say head, then this particular part, maybe the chest region, and this particular part, the hands, all these parts are a particular y, this small y, in a set y. So by the time you calculate each probabilities for the body parts, which actually is going to be greater than 0. So by the time we calculate for each body part, if you take the sum of each probabilities, it should be equal to 1. So the following slide shows an example of probability distribution of graph. So you can see here which is y in y. It is set. It is a set between 0 and 1, and it has two values and 1 degree of freedom. So let's see the next slide. Okay, in this graph, look at the probability distribution now. It starts from 0 and ends at 1. So probability is between 0 and 1. So if your probability is 0, it means we call it impossible event. So if your probability is 1, we call it a certain event. So let's say in maybe in December, probability is going to rain in December is, I can say 0.99. I might not be so sure that it's not actually going to rain, so because some things can happen. So if I say 0.99, it means I'm very, very sure. But if I say my probability that it's not going to rain in December is 1, it means I'm so sure it's certain to happen. It's certain to happen. This is a conditional probability. Any which way, for any x in x, p of y given x, by the time you take the summation over the set of probability, you're going to have a 1. Now, what does this guy means? Okay, for example, you can say, what is the probability that it is going to rain tomorrow, given that it's actually rained today? So you already know the probability of a particular event. Say you know it rained today. So let's say the probability that it's rained today is like 0.7. So now you want to calculate that, okay, what's the probability that it's going to rain tomorrow, given that it rained today? So you have something like this. P of y given x. X is already known. So in this case, you have something like what we call okay. So that will call something like this. Let me use this guy. So if I have a probability of A, so let me say P of I have P of A given B, for example. This is actually equals to probability of A intersection B all over probability of B. So this is formula for conditional probability. Now, in case where A and B, in case where A and B are independent, they are independent events. So let's say, for example, an example of independent events is, okay, let's say I should give Suzanne, I give Suzanne a coin that she should toss a coin. For example, she toss a coin. Let's say our first toss is a head. Now, if I should give Suzanne a coin again to toss, the result she's going to get in the second toss is not dependent on the first toss. They are two separate events entirely. So the result we are going to get for Suzanne tossing the coin in the second toss is not dependent on the first toss. So that kind of event is called an independent event. So in this case, probability of A given B. Okay, so that I will say probability of A given B in that case is going to be probability of A. So this is not dependent on the result we have in the first event. So in this case, what are we trying to say? So it actually means that if an event A and event B, if an event A and event B are independent, it means probability of A intersection B, in this case, is going to be equal to probability of A times probability of B. So this is times, it's going to be probability of A times probability. So let me just put a negation sign. So in this case, if probability of A intersection B is probability of A times probability of B, what's going to happen here? Let me write probability of A times probability of B. So in this case, this guy is going to cancel this guy. So you have probability of A given B to be equal to probability of A. So in this case, we say A and B are independent. So moving forward. A graphical model is a mathematical structure that consists of a set of nodes, which are called vertices, and a set of edges connecting the node. So formally, a graph G is defined by the following equation: G equals to B, comma E. B is the vertices, while E are the edges. So this is a finite set of vertices or nodes, where E is a subset of a Cartesian product between the vertices, is a finite set of edges, links or arcs. So you can have vertices A, B, C. Let's say A, B to E. Let's say you have can I rub up this part? I think I can. Hello.
Yes, you can.
Okay. Thank you. So, thank you. Is it raining in Abuja? Is it raining in Abuja? Because it's raining over here.
It is, the weather is, it's almost about to rain, and so the weather is dull.
Susan, is it raining outside?
That, for me, the network is a little not stable because of this.
Okay. Susan, is it raining at your end?
It has stopped.
Oh. So if is okay, so if is a set of nodes, let's say A, B, C. Let's say V has 3 vertices, and we said the set of edges E, the subset of the Cartesian product between V and B. So it means that E is a subset of A, B, C. Sorry, A, comma B, comma C. Because don't mind this writing. Because A, comma B, comma C. So what's the Cartesian product of these two? So you are going to have what you call the other pairs. So you are going to take the first A here. The first element here is A. You have A, comma what? Comma A. You start from the first element, so it's the other pair. So you have 2 points. So A, comma A. Then you still pick the first point here, then go to the next point. So you have A, comma B. A, comma B. Comma. You have A, comma C. Since you have exhausted the possible combination of A here, then move to B here. Then you have B, comma A, comma this B, comma B, and this B, comma C. Then you move to C. You have C, comma A, C, comma B, C, comma C. So that's the continue, dot, dot, dot. This is the cross product of V, comma B. So it means I'm saying that E is a subset, edges is a subset of this set. So I think you understand that part. Do we, Susan, maybe students will be the one to be responding to my question or something, so that I will know we are moving forward.
Why will I be the one responding? If I understand, I will. If I don't, I will say as well. So, what if the other parties don't or they do? I think everybody should respond individually.
Thank you. So it means E is the subset of the Cartesian product. This is the final set of edges into us. The graphical model encodes conditional independence assumptions between variables. It represents random variables as nodes or vertices, and conditional independence assumptions as missing arcs. So some other real-life examples of graphical models are roadmaps, electrical circuits, computer networks, because all of these have nodes, what we have free charts. So like say roadmaps. So if you are going somewhere, like for example, maybe you are going to work, your place, your home address, don't let me say home address, your house is a node. Now, when you leave your house, then maybe you are taking a personal car. Your house is a node. By the time you leave your house, you get to a point whereby maybe you turn to the right or turn to the left. At that point where you are turning, you come that point, like it's a junction, that's another node. Then you keep making turns until you get to where you are going. So their nodes are dependent. So look like you are following a Google map. By the time you get to a particular node, you hear an instruction that you turn to your right in the next 10 minutes at particular place. So that's a node. So they are all connected. So the example of graphical models, electrical circuits, computer networks, a network between maybe 3 or more computers. We have nodes are used to connect them together, stuff there. So types of graphical models, you have undirected and directed. So undirected is called Markov, and while directed are Bayesian networks. So undirected or Markov random fields, directed or Bayesian network. So undirected graphical methods. So a graph G is called undirected if for all A, B belonging to V. Now V is the set of vertices. So for all set of vertices A, B in V, so let me say all set of vertices. For all vertices A, B in V, V is the set of vertices. As you can see, as I explained here, V contain set of vertices. So A is a vertex, B is a vertex, A is a vertex, B is a vertex, C is a vertex. You have 3 vertexes. So for any 2 vertex in the set V, AB, this is an edge. So you see this is an edge. So A, B belong to the set E, which is the set of edges. Implies that B, A will also belong to the set E. So what is this whole grammar? So it means that if I have an undirected graph, if I have say A to be okay, say V is the set of vertices that has A. Let's say it has A, B, and C, for example. It means that the set E is going to contain. So if AB is in V, as in that statement, we are going to have A, B in E. We are still going to have B, A in E. So it means that you don't have any direction. There is no particular direction. That's why we got undirected graph. So as you can see in this image here, 1, 2. Since there's no direction, it means that I can go from 1 to 2. And I can also go from 2 to 1. So for example, maybe like this, there's this road in this my side that is Muritala Mohammed Bay. That leads to Oyibo. That place is a one way. So that kind of edge, we call it a directed edge or a directed graph. It means I can only go forward, I cannot come back. So you know, Nigerians used to break rules, you still see one way, people will still be coming the other way. So, but it's supposed to be one way, it's directed. But you see some roads whereby it is cars can be going forward and cars will also be coming back. So in that kind of case, you call that a kind of undirected graphical model in that case. So you can go forward. So you can go from 1 to 2. You can also go from 2 to 1. That you get. So that is just a layman expansion of that. Undirected graphical models are also called Markov networks. So MRF is an undirected conditional independence graph of a probability distribution along with the family of non-negative functions M. Or these ones are just are not necessary. So suppose that G is this guy, which is a set of vertices and set of edges. Here, vertex set B is equal to, so we have vertex 0, 1 to 6, and edge set, which is 0, 2, 0, 4 to this guy. So the figure shows an undirected graph. So from here, so maybe in an exam setting, you are given this. You are given this information. So you are now to tell, okay, is this an undirected graph or not? Will this form an undirected graph or not? So first of all, check. You have 0, 2 in the edges, in the set of edges. Do you have 2, 0 there? Okay, you don't have, no. Okay, check this guy. 0, 4. Do you have 4, 0? Yes. So you can see this is an example of undirected graph. So you can go from 0 to 4. You can also go from 4 to 0. So if you can find at least one, then you have to say it's an undirected graph. I think that you can see you have 3, 6, you have 6, 3 here. And you can find those examples there to identify that in directed or undirected graph. So let's look at some terminologies in this regard. So adjacent node. Now, a node B belonging to V. So B is a vertex or a node. Is called adjacent to a node A, which also belongs to V, or a neighbor of A. If and only if, that is, if and only if there is an edge between them. Say AB belonging to E. So it means I can go from A to B. So if I have an edge that leads me to, so let's say from this guy. So from this guy, so 0 and 1, the adjacent. I can go from 0 to 1. Set of neighbors, the set of all neighbors of A, which is called neighbors A. So the set of all neighbors of A, called neighbors A, is equal to the set of B, the set of node B in V, such that this bar is called such that. So it's calculated as such that. So when you use this kind of brackets, curly brackets, it's used to denote a set. So that's why I said neighbors A is equal to the set of node B belonging to V, or vertex B belonging to the set of vertices V, such that AB belongs to E. So the set of neighbors A is sometimes called the boundary of A. So what is this in essence? So let me use this graph to explain to you. So this 0 is a neighbor of 1. This vertex 10 is a number of 1. This 2 is a number of 1. So the set of neighbors of 1 is 0, 10, 2. So you have you can answer neighbors of 1 is, you can see that it said B belongs to B, so that AB belongs to E. So because we have, these are edges. These are edges. Degree of node. Now the degree of a node A, which is number of incident edges, is degree deg A. Should know that degree of A is equals to the absolute value of neighbors of A. So what are we trying to say here? Is just you are just trying to count the numbers of neighbors that A has. Then you can say, you can call that the degree of node of a particular node A. So closure of A, so closure of node, the boundary of A together with A is called the closure of A. So closure of A is neighbors of A union A itself. So we talk about the number of A's already. So connected nodes. 2 distinct nodes A, B belonging to B are called connected in G if and only if there exists a sequence C1, CK, where all these are distinct nodes called a path. Now the starting point is the A and the finishing point, which is the CK, is the B. All these ones are just mathematical jargons. Where CI and CI plus 1 belonging to edge, belonging to E, say they are connected, are called connected nodes. So what is let me see whether I can use this. We have to explain what I'm talking about. So let me just use a layman example. Yes.
Before you give the example, can you distinguish between the connected nodes and the adjacent nodes? What's the difference?
So adjacent nodes is just okay. If I can get to node, if I can go to maybe, so let me use this example. If I get to 1 to 2, right? If I have an edge that leads me from 1 to 2, you can say 2 is a neighbor of 1. You can say 2 of our adjacents or their neighbors. So in this case, 2 is a neighbor of 1, 1 is a neighbor of 2, any which way, because it's not directed. Okay. Now, connected node is that, okay, if I'm going to office, from my home or from my house, okay, I can pass Mushin to get to my office. I can pass K2 to get to my office. I can pass Ikorodu to get to my office. So you have different locations whereby you can get to a particular destination. So K2, Ikorodu, and which one did I mention again? I mentioned K2, Ikorodu, and Mushin. So K2, Ikorodu, and Mushin are the nodes that are in between C1 and CK.
Okay.
C1 here is my house. CK is my office. Now, Mushin, Ikorodu, and K2 are the set of points whereby I can get to my workplace. So I can take any of those set of points to get my destination. So I can pass through all those paths. So you can say that my workplace and my house, they are all connected. They are connected. So they are connected nodes. So for example, I don't know, this one is kind of, so look at from 0 to 1 like this. I don't know, from 0 to 1. So we have, how can I get to, okay, further I'm going, suppose I'm going from 0 to 1. I can pass 0 to 9, 9 to 10, and 10 to 1. I can try to go, okay, 0 to 9, 9 to 10, 10 to 2, 2 to 1. In that regard, so I can pass different parts. I can go to different parts to get to 1. But look at, I cannot go from 0 to 9, 9 to, look, I can go from 0 to 9, 9 to 4. Maybe I can pass from 4 to 8. Maybe to come back to 9 again. Then shall get to 1. So there are different parts which I can get to a particular point. So you tell those 2 points are connected using those particular nodes.
Okay.
So let's talk about a tree. Another directed graph is called singly connected, or a tree, if and only if any pair of distinct nodes is connected by exactly one path. So another directed graph is called singly connected, or a tree, if and only if any pair of distinct nodes is connected by exactly one path. It simply means that I can only call this graph a tree if and only if the way I can go from 0 to 1. So if I'm going from 0 to 1, I can only pass through this path, this particular path. So there's no way I can come from maybe 0 to 12, go to 0 to 3, then go to 0 to 2, then get to 1. It's only one path I can pass to get to a particular destination. So you call that kind of graph a tree in that regard. We have what we call subgraph. So another directed graph G of x equals to x, comma the edge of x is called a subgraph of G induced by x if only if x is a subset of V and the edge of x is actually the Cartesian product between x and x that forms that intersect in E. That is, if it contains a subset of the nodes in G and all corresponding edges. So let me see whether I can explain this. So let's say you have a particular graph, another graph. So you can say one graph is a subgraph of a particular graph if, for example, the set of vertices in, so you have graph 1 and graph 2. So you are saying graph 2 is a subgraph of 1. So, so if the set of vertices in graph 2, say x. So if x, the set of vertices in x is a subset of V, so let me say, let me come here. So in layman, I'll just say, so if you have a graph 1, which have the set of vertices to be V, say, so let me say, I have A, B, so let me do this, A, B, C. So this guy has this set of vertices, A to E. So and I have a graph 2, which has the set of vertices X. So X has this set of vertices A, comma B. First of all, the first condition is satisfied, whereby because X is a subset of V. Why? Because the set of vertices I have here are also in this guy. So A and B are in this guy. So the first condition is satisfied, which is saying that it's a subset if it contains, if and only if X is a subset of V, and the edge of X is equal to what? X, the Cartesian product between X intersection E itself. So let me just write that down. X plus X intersection E. So this is called the edge of X, right? Don't mind the way I'm writing it. So if the edge of X is called X plus X intersection E, that is, so you can explain with this. So you are saying that okay, G2 is a subset of G1. If this guy is a subset of B, okay, it's satisfied. Now, what is the edge? What is the edge? Don't forget that the edge is what? Is V. The way I'm writing it should not look like X. Is V, the Cartesian product of V cos V, right? Now, so this, what's the edge of X? The edge of X is going to be what? Can someone answer me in the class? What will be the edge of X? Given that X is this, what's going to be the edge of X? Can someone answer? So let me put this one this way. Let me put a bracket here. Can someone answer? What's the edge of X now? So if nobody wants to answer me anyways. So edge of X is X cos X as the cos product of X. So that would be what? That would be the set of A, comma A. So the Cartesian product between A, X itself and X itself. So A, comma B, B, comma A, B, comma B. So if you have this guy, so let me say continue like this. If you have this guy, intersection P itself, which is this guy, to be equal to edge of X, then you can now say this guy is a subgraph of G1. So this guy, you can now say this guy is a subgraph of this. So if those two conditions are satisfied. Let's look at a complete graph. An undirected graph G is called complete if and only if its set of edges is complete. That is, if and only if all possible edges are present. Or, formally, if and only if E is V cos V minus A cos A such that A is in V. So so let me just give an instance so that I won't be getting guys confused or bored about this. Now, this guy is not a complete graph. So why is this guy not a complete graph? The reason is that you can have different scenarios where you can use to compare. Why? Because I don't have 0.8 as an edge. There's no way I can go directly from 0.8. This is another illustration to show that it's not a complete graph. I cannot go from 3 to 4 directly. This is another example. I cannot go from 3 to 5. So I should have all possible combinations to show that it is a complete graph. So that's just a logic. Click. A complete subgraph is called a click. Okay, complete subgraph is called a click. So I think that's even gives all the definition you actually need. So if we have a subgraph, now if the subgraph is now complete, you now say it's a click. Using the definition of subgraph, so if G1 is a subgraph of G2, now if G1 is now a complete graph itself, then you say you have a click. That is, if G1 has all the possible edges and G2 has all the possible edges. So G2 is the subgraph. So if it has all the possible edges, then say it's a click. So let's look at directed graph. This illustration they give, don't mind them. There's supposed to be arrows here. There's supposed to be arrows. And let me see whether the next test shows that. So they didn't do that. There's supposed to be arrows. I don't know why they didn't put arrows. I don't know where I can. Do you have your material with you? Do you guys have your material with you?
Which of them?
You are in book 2 already.
I don't have my book 2 with me.
Which one do you have? Which one do you have, sir?
I left my book 2 in the office.
Susan, do you have your book 2 with you?
Arrows are there in the book.
What did you say?
Well,
You don't have it with you?
the arrows were indicated in the book. Yes, I do. I have it.
Okay, the arrow is indicated in the book.
Oh, yes.
That's what I'm referring to the book. But even the graph in the book is quite different from this one.
Yes, from this one.
That's why I'm asking whether you guys have the book so that we can get
Not the same.
So no problem. The graph G is called directed if for all A, B belonging to B, A, B belongs to E implies B, A does not belong to E. So what is this guy saying? What this guy is saying is that if I'm going from A to B, if I have, if I have an edge that leads me to B from A, I shouldn't have an edge again that will lead me from A to B back again. So that's that illustration. So let me give let me demonstrate this illustration using the whiteboard marker. So if I have a set of vertices V, so if I have a set of vertices V, say V is equals to this set of vertices. It has A, B, C, a set of vertices. A, B, C. A, B, C are in V. Now the set of edges I can have is going to be a subset. So let me put a subset of. Now I can have we used to use V cross V. Now, first of all, let me write the possible examples of V cross V for us. What is the possible combination we can have? We can have A, right? We can have A, B.
Okay.
We can have AC. We can have BA. We can have BB. We can have BC. Don't mind this, the way I'm writing this thing. We can have CA. We can have CB. And we can have CC. So I will close it here. Now, what this guy is saying that if A, B is in V, AB belonging to E implies that BA cannot also belong to E. So it means that if you have an edge AB that is in the set E, I cannot add BA again. Okay. If I have a set AC belonging to E, I cannot have CA. So that's what that guy is saying over there. So if AB belongs to B, it implies that BA cannot belong to E. So in that case, you say you have a directed graph. So and AB is considered to be directed A towards B. So directed graph methods are also called Bayesian networks or Bayes net. So a Bayesian network is a directed conditional independence graph of a probability distribution along with the family of conditional probabilities of the factorization brought by the graph. The Bayesian network is based on what we call the Bayes theory. So what's the Bayes theory? I think we are going to see as we proceed. So suppose matrix set V is equal to this guy, and edge set E is equal to this. Typical shows a directed graph created with the same data set as used for plotting undirected graph. So this guy, there's can't have this guy to be an edge. 0, 4 is here. I cannot have 4, 0. I cannot have 4, 0. So, this guy is not supposed to be there. In this case. So 3, 6, I cannot have 6, 3. Let me see. Let me go back to that slide. How many points do you have in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let me go back to that first one that we did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But this one is 13. Is it? Okay. It's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So they didn't change anything here. So what they are supposed to move is, if I have 0, 4, I'm not supposed to have 4, 0. If I have 3, 6, I'm not supposed to have 3, 6. So that's the difference between directed and non-directed graph. I hope that is understood. Okay, I'll take that as a yes. Let's look at some terminologies under this guy. You have parent and child node. A node B belonging to B is called a parent node. A parent of node A belonging to B. And conversely, A is called the child of B if only if there's a directed edge from A to B. So from B to A, that is, if only B, A belongs to A. B is called as to A if only if all this one is just mathematical jargon. So let me just explain what we are saying here. So if I have, let me just look up this guy. If I have this graph, so if I have a node A and a node B here, and I have this edge in between them, I have this edge with an arrow. A here is the parent, B here is the child. As simple as that. So D connected nodes. Two nodes A, B belonging to B are called D connected in G if and only if there is a sequence C1, CK of this thing called a directed path with C1 equals to A, CK equals to B for all I blah blah blah. So this one is related to all connected nodes in undirected graph. It's just that this one has direction. So connected nodes. Two nodes A, B belong to B are called connected in G. If there is a sequence C1 CK of distinct node called a path for all CI plus 1 belong to V, or CI plus 1 Ci, so not belonging to V, sorry, belonging to E, or Ci plus 1, comma Ci belonging to E. So what's the difference between this one connected node and disconnected node? The difference is that if I have a point A and I'm going to a destination B, the connected nodes, I will only follow a particular, I will pass some specific paths for me to get to B. So those paths I pass through to get to B. So let me just put something. So let's say this is A, this is B. I have a point C1, a point C2. Now, if I can go from here to this place, and from here to this place, and from here to this place, then I say I have a disconnected node. But in case whereby, okay, I can have a C3 here. Then I go here, and I can go here. So this is an extension of a connected node, not a disconnected node. A disconnected node. Here, now, I can go from this place to this place, this place to this place, this place to get to B. And I can otherwise go from here to here, here to here, here to here. So I have different paths I can take. But this one, for in disconnected, I have just a single path. So that's just the difference between both of them. So let's look at polytree. A directed acyclic graph is called singly connected or a polytree if only if each pair of distinct nodes is connected by exactly one path. If and only if each pair of distinct nodes is connected by exactly one path, meaning I can only go from A to B by just one single edge. Okay, let me see. So let me go back again. If only if each pair of distinct nodes is connected by exactly one path. So let me use this guy to so let me use this guy too. Now this guy is not, I think let me go back. Let me talk about a tree, then I'll talk about the difference between these two. Okay, let's see. A directed acyclic graph is called a directed tree if and only if it is a polytree. Exactly one node, the root node, has no parent. Exactly one node, the root node has no parent. Now, in this place, this guy is called a poly. This guy will only be a polytree if I remove this point C3. If I remove this point C3 from here, let's say I erase this. It means I can only go from A to B using this specific path. But if I should include this C3 here, it means I don't have one path again. I can go from A to B using the path, going from A to C1 to C2 to to B, or A1 to C1 to C3 to C2 to B. So I have more than one path. So it's no longer a polytree. Now, in the second scenario, it's called a tree. If it's a polytree, first of all, check, is it a polytree? If yes, okay. Check the root node. Does it have a parent node? Does it have a parent? So let's say this is a graph now. This is not a polytree, so I have to remove this guy. So the root node, so what about the root node? That is where I'm starting from. This is the starting point. This is the root node. Does this guy have a parent? No, because it is not coming from, it's not this guy is not picking, he's not a child to any node, say V or say E. So this guy is not dependent on anybody. So that's when you say this guy has no parents. So it does not depend on anybody. So when you say someone has a parent, it means, so that has come to a relationship of parent and child. The child is dependent on the parent. So it means that, what it means that this guy, before I can get to this guy, it means that I must pass through A. So that's why this guy is called the child and this guy is called the parent. Because this guy that is B here is dependent on this guy. I cannot get to B without going through A. So that's why this guy is the child and this guy is the parent here. I guess we are making sense. I hope there will be much time, sure. Someone wants to talk. Okay. Conditional independence in graphs. In a conditional independence graph, each vertex or node represents an attribute to describe the domain in study, and each edge represents a direct dependence between two attributes. So a graphical model extracts conditional independence relationship between variables from their parametric forms. So this guy shows a pictorial structure for articulated post estimation. So here you are saying that, okay, the head, now the head, you have the head, the top can be maybe the cloud or something. Then you have the head. Now the torso is dependent on the head. I don't know the torso, maybe I think this chest region you're talking about here is dependent on where the head falls in. Then this guy is dependent on what we call left arm and the right arm. So this guy is dependent on where the right arm is positioned. So what am I saying? The torso is dependent on the head. The right arm and the left arm is dependent on the torso. So where the torso is, so it depends on where the left arm and the right arm is going to fall. Then you have what we call the right hand, which is going to be dependent on the right arm. The left hand is dependent on the left arm and stuff like that. So that's that. We might not be able to cover much, talk about all of this. So we actually need to read our material. Actually, read our material. So you can read about this. I will just go to the next slide because of our time. Okay. Let's see. Because I have to just. Here's the version. Okay. Applications of graphical models. Graphical models are successfully applied in several areas like manufacturing, finance, steel production, handwriting recognition, telecommunication network diagnosis, object recognition and images. Let's look at a case study of application of graphical model at Volkswagen. So the Volkswagen Corporation offers each customer the option of configuring their cars as individually as possible. So what's the problem? To attempt to achieve the ideal situation in which the customers are provided customized products built using components that arrive just in time for assembly, so that no stock is necessary at all. So what's the solution? Volkswagen adopted the idea that given certain properties, others may be selected independently of each other, thus making a decomposition of the joint probability distribution possible. So based on this decomposition, Volkswagen estimated the frequency of relevant combinations of properties. The system assumes that all cars in the sales database have these combinations. The decomposition allows Volkswagen to remove repetition individual configurations, and therefore enlarge the samples that could be evaluated. So the thing is that, okay, I want to configure my car. So I want to configure my car individually. Okay, I have some stuff I want to add to my car to customize it some way. So based on certain suggestions by the customers, then they can make some do some combinations, and okay, I think this person would like to have this kind of customization for the car or stuff like that. So they don't want to keep components just in stock. so they just want to, they don't want to have components just in stock. So maybe we have different parts of components, A, B, C, D, E component. So let's say if I want to customize my product, I just need A and B. Another person might just need A and C. Another person might need C and D to customize the component. Another person can need B and E. Now, if you just, okay, if you decide that you want to buy, okay, these are the components that is needed for customization. If you decide, okay, I want to buy 100 of this in uniformly, 100 of these components, 100 of these components. So I have 500 components. But then, if others should come in, maybe depending on the orders, I might have that I will use more of A than more of E. Even the list I might use in E, maybe it will just be maybe 20. Then I would have used up A and B, and there will still be like 80 of E. Then I have to order more of A. Then this one will just be stuck there without use. So I don't want a situation where I just have components in stocks. So I'll use the let's say the suggestion of certain customers and make combination of properties, possible combination of properties I can add for a particular customization, and order for those components based on those properties, rather than just having to get components uniformly and say, okay, let me just get 100. So it's based on those combinations that will make my order, so that I won't have components in stocks. So I won't have no stocks necessary at all. So where is it? So that no stock is necessary at all. So that's the idea. So finally, both are computing the supply of individual components from this estimate to build the graphical model. Both are created a relational network based on catalog of technical and marketing rules to describe constructible cars. So so the catalog of technical and marketing rules is translated into relational representation. All rules that refer to the same set of attributes or property families are represented by a relation. Starting from the Cartesian product of attributes domains, all tuples are discarded that are incompatible with one of the rules. So let's say I want to customize a particular car. So then now I will have different combinations based on the components I have, but some certain combinations won't work for the customization of a particular car. So based on the rules I have set down, those rules that those combinations that are compatible for that particular car is being discarded, stuff like that. So moving on to the next slide, without asking much of our time. Now let's introduce us to Bayesian statistics. As you can see, Bayesian statistics is based on Bayes theorem. And what does so Bayes theorem enables users to update the probabilities of unobserved events, given that another related event has occurred in the past. So in this case, we have what we call the conditional probability. So in this case, you can say maybe football prediction. So Man City played a match last week and they won 5-0. So what's the probability that Man City is going to win the match this week, given that they won 5-0 last week? So this kind of stuff. So let me just search for Bayes theorem. So you have an idea of what Bayes theorem. I see it from myself. So in probability, Bayes theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. So you can see here probability of A given B. The answer is probability of B given A. That's probability of A, probability of B. B is somehow done over in data. Let me see. That theorem is stated mathematically as the following equation. So P of A given B will now be P of B given A times P of A over P of B, where A and B are events, and probability of B cannot be equal to 0. Cannot be equal to 0. So once we list probability of a particular event A, given that a particular event B has occurred before. So if an event B has occurred before, I can have probability of B to be equal to 0 because that's an impossible event. You cannot have an impossible event in this regard. So let's look at for example here. Suppose a particular test or for whether someone has been using cannabis is 90% sensitive. Meaning that so probability of user given positive is probability of positive given user, that's probability of user following this formula, probability of being positive. Now, yeah, what do you have here? Probability of positive given user, this kind of manipulation. Do let me bother with this. So it's just based on the conditional probability. So Bayesian inference is based on the data that already occurred and not on data that could have occurred or but did not. So in this case, we say impossible event but did not occur. So Bayes theorem finds the posterior density of parameters per given data. It combines information about the parameters from prior density with that from the observed data contained in the likely function model. All these things are so. A Bayesian network is marked cyclic graph that represents a joint probability distribution over a set of random variables V. Format is given as this, where B is Bn, G is the directed acyclic graph which we talked about. We refer to directed acyclic graph to be Bayesian network. So whose nodes x1 to xn represent random variables, and edges represents direct dependency between these variables. So G encodes independence assumptions by which each variable xi is independent of its non-descendant. So this symbol represents the set of Bn parameters. So without having to bother us about all these mathematical jargons. Let's move to the next slide. So example of beings. Suppose you want to determine the probability of a grass being wet due to rain. So consider the BN in the figure. Weather has three states: sunny, cloudy, and rainy. There are two possibilities for the grass to be wet. For the grass, wet or dry. So the grass can be wet or be dry. And the sprinkler can be on or off. So if it is raining, the grass automatically gets wet. Very good. If it's sunny, if the sunny weather persists for a long period, then the grass can be made wet by pouring water from a sprinkler that is turned on. So a grass being wet or dry is depending on maybe it's raining or the sprinkler is being turned on. So when the actual probability of being reflects the actual weather, lawn and sprinkler use behavior. So the BN can answer such questions so that, okay, if the lawn is wet, what is the probability that it was caused by rain or sprinkler? So if the probability of rain increases, how will it impact the use of sprinkler to water the lawn? So suppose the grass is wet, that this is because of either of the following causes. It is raining or the sprinkler is on. Okay. Characteristics of Bayesian network. So graphical models so these include explaining away, top down and bottom reasoning, causality, conditional independence in BNs with discrete and continuous links, and circular order. Are you going to speak about all of this? So let's see whether we can talk about all of this in the next slide. So let's talk about explaining away. In the water sprinkler example, so the two causes, which is sprinkler or rain, compete to explain the observed data. Therefore, S and R become conditionally dependent, given that their common child, W, is observed. W means wet. So even though they are marginally independent, this phenomenon is called explaining away because either cause is sufficient to explain the fact on W. Because the gas being wet can either be caused by rain or the sprinkler is on, whether the sprinkler is on or off. So, bottom up and top down reasoning. Now, in this case, BNs are often called generative models because they specify how causes generate effects. So in water sprinkler example, you have an evidence of an effect which is wet grass. Now, and you inferred the most likely cause. So this approach is called bottom up. So when you are going from the effect to the cause, you call that one bottom up. Now when you are going from cause to effect, you call it top down reasoning. So bottom up or diagnostic reasoning, because it goes from effect responses to causes, which is predictors, and creates a kind of inverse probability. So what do we call it? Diagnostic reasoning. Just like, okay, they killed someone today. They killed someone. Now the person is already dead. They are not trying to see what could have caused this person's death. That one they are doing diagnosis because the thing has already happened. They are going from what you can see, what has already happened, and what can cause this to happen. So on the other hand, if you calculate the probability that the grass will be wet, given that it is cloudy. Then the approach is called top-down or causal reasoning. So in this case, you can say, okay, oh, they are fighting in motion. What's going to be probability that, or they are shooting in motion, or I should have, okay, they are fighting this in the first street, maybe the back of your street. What probability is that the fight is going to reach my street? Does not happen, but you are looking at the cost. What's going to be probability that this fight is going to get? Or let me use this example. NEPA is at the back of your street. So what's you ask for beans or to cut off your light. Cash. This is supposed to be causality, not casualty. But the way that's the way they even wrote it in the casualty is supposed to be causality.
Imam?
Stop.
Is causality.
So okay, yeah.
Causality.
So, it's supposed to be causality, not casualty, yes. So causality discussions are used to explain the cause and effect of a phenomenon. So BN can be used to give a solid mathematical foundation to causality discussion without an experiment. So we have conditional independence in BNs to explain the conditional independence relationship encoded by BN. We now have what we call the bias ball algorithm, which can be used in this case. So the algorithm says that two sets of nodes A and B are conditionally independent given a set C. If only there is no way for a ball to move from A to B in the graph. So he said they are conditionally independent. So I cannot go from A to B if there's no way for a ball to move from A to B. So the essence is that there's no edge that connects A to B in this case. So BNs are with discrete and continuous nodes. So the water sprinkler example use nodes with categorical values and multinomial distributions. User can also create BNs with continuous valued nodes. The most common distribution for this variable is Gaussian, as for continuous case. For discrete nodes with continuous variants, the logistic or softmax distribution can be used. Temporal models are directed graphical models of stochastic processes. They are also known as dynamic BNs. So the simplest DBNs we have is the Eden Markov models, linear. You don't need to. All these are just statistical grammar, stochastic processes. So linear dynamic systems. So HIM is the HIM that has one discrete hidden node and one discrete or continuous observed node per slide. HIM consists one hidden and one observed nodes in each slide. Okay, that's how it's supposed to be. So these nodes include one discrete and one discrete or hidden node. So you have one hidden node and one hidden node and observed nodes in each slide. linear dynamic systems and Kalman filters. So let's see. An LDS has the same topology as HM, but it's assumed to have all the nodes in linear Gaussian distribution. The linear Gaussian distribution is shown as follows. So in this case, I think the difference between this guy and this guy is that this one, I go from this state to this state to this state, but each CD node has just one observed as it is here. But here, I can connect to this observed. This one can connect to this. So it's more complicated than that of the HMN. Let's see. Probabilistic inference in Bayesian networks. Given a hypothesis, BNs are used to estimate probability that the hypothesis is true based on evidence. So you have deducing unobserved variables, parameter learning, and structure learning. So more details are not given on this. I think let me see whether the next slide to does that. So let's check it next time. So the first one is deducing unobserved variables. A BN is a comprehensive model of variables and their relationship. BN can be used to find the state of a set of variables when evident variables are observed. Okay. So this process of estimating the posterior distribution of variables, even evidence variables, is called probabilistic inference. Popular inference methods are called variable elimination. So this process removes unobserved variables one by one by distributing the sum over the products. This process of removing unobserved variables, unobserved and useless variables in a step-by-step approach by taking addition over the multiplication. So excuse me for 2 minutes. So, okay, variable elimination is the process of removing unobserved and useless variables in a step-by-step approach. Click tree propagation. This method inserts the computation, which allows simultaneous querying of several variables and rapid propagation of new evidence. So we can read more about these inferences. Recursive conditioning. This method allows a trade-off between space and time. If sufficient space is available, it's equivalent to the variable elimination method. You have parameter learning, structured learning. But okay. But now to bother ourselves about all this information anyway. Just have in mind the types of references we have, which is deducing unobserved variables. What are the three ones we have? Parameter learning and structured learning. Okay. These are the three. Let's see. Okay. Okay, here we talk about Bayesian methods. So you can use Bayesian methods to sum over a joint probability distribution in Bayesian network, while variable elimination, dynamic programming, and approximation algorithms. Then, okay. So in variable elimination, in this you can use the factor computation of the joint probability distribution to do the effective marginalization. In this method, you can sum out the relevant terms using this. Then we can read about dynamic programming, approximation algorithm. Might not necessarily need to bother yourself because there's so much information. Unless you want to delve into machine learning, this part of machine learning anyway. Okay. So let's look at the application of Bayesian networks. So some common applications of Bayesian networks are gene regulatory networks, medicine, environment monitoring, document classification, information retrieval, semantic search, image processing, gaming, engineering, data fusion, also and everything. Okay, I think that's all for the Bayesian network part. I'm trying to cover much of this, then we can go to the lab. So I'll first of all cover the Bayesian network and the neural network theory session, then go to the lab, then finish up on them. So I think I'm done with this part. So let me go to neural network. Do we have any questions so far?
No.
Okay. So what are we trying to do in this regards? To explain the basics of artificial neural network, applications of neural network, explore the structure of artificial neural network with the help of simple examples. Okay. Explain models of artificial neural network, learning rules, illustrate training algorithms, and implement neural networks in R. All right. So artificial neural network. So simply neural networks are computational algorithms intended to simulate the behavior of biological systems composed of neurons. So a neural network is an oriented graph consisting of nodes, which in the biological analogy represent neurons connected by arcs, which correspond to dendrites and synapses in biology space. The training stage is performed by analyzing in sequence the observations contained in the training set, one after the other, and by modifying them after every iteration. So they are implemented not only for classifications, but also for regression of continuous target attributes. We find great application in data mining using sectors like economics, forensics, forex, and stock exchanges. So carefully trained neural networks can identify patterns in data, and those trends can be used in making predictions. Now, so it's a machine learning algorithm based on the model of a human neuron. So the human brain consists of millions of neurons that transmit and process signals in the form of electrical and chemical signals. They are connected with a special structure called synapses that allows neurons to pass signals. So you have neural network learning, predictive and descriptive. So the predictive part is supervised, where the descriptive part is unsupervised. We talked about supervised and unsupervised machine learning in the last class. So what are the layers you have in neural networks? You have the input layer, you have the hidden layer, you have the output layer. So this figure illustrates that. So this is the input layer, which usually is the number of variables you have in your data set. Then you have hidden layers whereby some we call it functions are being applied to the input to generate an output. Sometimes there might not be hidden layer, right? So the input layer, the purpose of the input layer is to receive as inputs the values of the explanatory attributes for each observation. So usually the number of inputs is equal to the number of explanatory variables. So hidden layers apply given transformations to the input values inside the network. In the hidden layer, each node is connected to incoming asks that grow from other hidden nodes or from input node directly. So it is connected with outgoing asks to output nodes or other hidden nodes. Then you have the output layer, which is simply connections from the hidden layers or from input layer and in turn an output value that corresponds to the position of the test value. So in classification problem, there is usually only one output node. Let's take a look at that. Advantages and disadvantages of neural networks. So first of all, it performs well with linear and nonlinear data. Works even if one or a few units fail to respond in network. It learns from the analyzed data and does not require retrieval. So what are disadvantages? Need training with sample data to operate. Requires high processing power. Refers to black box models and provide very little insight into what models really do. So sometimes, so let me use linear regression and neural network as an example. For example, linear regression, you're like, okay, y is equals to, that's a simple linear regression. Y is equals to a plus bx, blah, blah, blah. So if you really know what it's actually doing, but in neural networks, you don't really know, you don't really know what's really going on. You can't really tell, or you have an intuition of what's going on, but you can't really tell what's the model is actually doing. So the difference between neural network and a regression model is that it finds any way to just solve the problem. Regression, there is a way you are following the formula y equals to a plus b. But neural networks, any way is a way. So, for example, if I'm living in my house and I'm going to office, my own usual way is to pass through Sabo. From Sabo, I take maybe Oyibo, they drop at the office or something. But in neural networks, my goal is to get to the office. Anywhere I pass to get there, it's none of my business. My own is just to get to the office. So that's just the difference between a neural network and a regression model. So and that's one of the constants. Yeah, importance. Now, okay, look at this. A neural network is shown in the following figure. For node A to D. So I know I'm not really talking much about this, but using the knowledge of what we did in Kafka models, you should be able to everyone that Bayesian network, you should be able to understand why we have this result. So for a node A to D, the minimum connection weight will be what? So who can tell me why this result is actually 3? Are we still there?
Again?
Except for node A to D, the minimum connection weight will be what? They take 3 to be the answer. But why is it that the answer is 3?
So, but why not we go straight from A to D?
Now the question is, from node A to D, the minimum connection weight will be what?
Oh, weights. Okay, weights are attached to.
Yes.
Okay. Now, why? So what about 1, which is A to C?
One, I don't understand.
I will say the answer should be 4 because you have to move from A to C, then C to D. That gives us a weight of 4 compared to the weight of 7 from A to D.
Okay. Susan, are you there?
Yes, I am. I am here.
What's the answer? What's the answer? Or what should be the answer? So let me put it down. And why is that?
Sorry, does that mean something? It said A to, you rather from A to C before D, right?
Mm.
But this is D now. There's an arrow from A to D, right?
But it has a weight of 7.
It has what?
It has a weight of 7.
Oh. I don't know. I don't know why it's 3.
Temba, are you there? Let me check. The file is still on hold. So, okay, let me ask you a question. From A to D, look at the model. If you look at the graph very well, what are the possible paths you have from A to D?
From A to D.
You have A, C, D,
D,
A, D, and then A, B, D.
Okay, let me write it down. Okay, he said we have AD, Abi.
No. Okay, I got it right. It should be A, C, G, D. A, C, G, D.
Exactly.
A, C, G, D. Yes, it's 1, 1, 1.
Because so you have A to C, C to G,
and G to D.
You have
Yes.
1 and 1.
1.
And that's the minimum weight you have.
Yes.
Susan, did you get that?
Okay, from A to C, that's one. From C to G, that's one. Then from G to D, that's another one.
That's one, exactly.
Okay, minimum. Yeah, I got that.
Okay. So first of all, we take a look at very well before we come to conclusion. All right. You can move on. So, application of neural network, handwriting recognition, traveling sales problem man, image recognition, stock exchange prediction. Oh my. So in handwriting recognition, we have to recognize characters. The bitmap of handwritten characters are passed as bit, and correct characters and digits are provided as output to feed forward neural network. So we have some samples of data that speak to the model. So it looks through the samples and compares, okay, this transformation, and okay, this should be two. Let's say we fit some samples into it, and look at the samples and okay, I think this should be two, okay, this should be three, to identify the characters. The user have to train the neural network by preparing the handwriting samples to the network. Traveling salesman's problem. The traveling salesman problem refers to finding the shortest possible path to travel all cities in a given uh, area. So in neural network algorithms such as genetic algorithms start with random orientation of the network to solve the problem. So what does this algorithm do? It chooses a city randomly each time and finds the nearest city. So this process continues several times and results in formation of a rig around all the cities. So the use algorithm minimize the length of rings. So I'll just pick, okay, particular city at random, find the nearest city. So the nearest city we have a ring around it. So it means if I have, let me just go on. So if I have, if I have city A, if I'm pointed at city A like this now, I'll just find the nearest city. Okay, and I'll draw an edge, like a straight line. Okay, this is the nearest city. So you can use Euclidean distance in that case. So then I pick another random city, find the nearest city, then it continues till all cities match. Then the algorithm is just to minimize the length of link that you have. You have image compression, stock exchange ratio. So in image compression, we have a network used for image compression contains equal size of inputs and output layer, and an intermediate layer with smaller size. So the ratio of the input layer to the intermediate layer is called the compression ratio of the network, which is calculated using this formula, which is input layer over intermediate layer. It can be used for stock exchange prediction also. So consider the following measurements for the size of layers in a neural network. We have input layer to be 36, output layer to be 16, so intermediate layer to be 16, and output layer to be 108. Suppose the network is designed for the image recognition, which of the following values represent the correct value of compression ratio for this network? All the formula for compression ratio, they have to be input layer over intermediate layer. This over this is not 2. Maybe they wanted to write 32.
Yeah, maybe we can.
So that's by the way. Structure of the neural network. The structure of the neural network also describes its architecture or topology. Consists of number of layers, elementary units, interconnections, weight adjustment, and mechanism. So the simplest structure is the one in which units are distributed in 2 layers, just input and output. But then you have 18 layers, then is more complex. So each unit in the input layer has a single input and a single output. The output unit has all the units of the input layer connected to its input with the combination function and the transfer function. So the predictive power of a neural network increases with the number of hidden layers and units in these layers. So you should take note of that. Whether or not a hidden layer is present, the output layer of the network can sometimes have a number of units when there are a number of classes to predict. So this will show a simple neural network. You have the data, then you have the input layer, then you have the output layer. And these are the inputs. You have the transfer function. P of 1, P of 2, and less of that. So moving on to the next slide. For this one, you have the hidden layer. You have the input layer, you have the hidden layer, you have the output layer. So in this case, it's not going directly from the input layer to the output layer. Just pass through. So hidden layers, which makes it more complex than just the normal simple neural network. But in this case, this one we have one output layer. Here we have 2 output layers. Now, Mr. James is a data analysis scientist in a FMCG company. He wants to build a neural network to analyze the purchase trends. To improve the accuracy of the neural network, he has decided to add a hidden layer between the input and the output layer. You know, we said, let me go back to it again. Okay, it's in the previous slide. The accuracy of a layer increases with the number of hidden layer anyways. So the to improve the accuracy of the neural network, he has then add a hidden layer between the inputs and output layers of the neural network. In this network, the hidden layer should be smaller than the input layer and larger than the output layer. To improve the accuracy of the neural network, he has then add a hidden layer between the inputs and output layer of the neural network. In this network, the hidden layer should be smaller than the input layer and larger than the output layer. So let's take note of that. Okay. So, but when your hidden layer is like even you cut your input layer or even more, then you tend to have what we call overfitting. Overfitting, but it's supposed to be smaller than your input layer. Artificial neural network models. So models of artificial neural network, we have multi-layer perception, media business network, the Cohort network. Might not be able to. Let's see if I can go share. Yes, sir.
Can you go back one slide or two to that input layer and output? No, not back, back again. Okay. It's okay. I was expecting that the input layer is the same thing as the data. What's the difference between the data here and the input?
The data here is just like your Excel data. Then the input is just the number of variables, the expansion variables you are considering here. Like the columns we have the data.
Okay. But anyway, as a layman, I was thinking that the data should be the input.
And the data is the input, but you have different variables in the data. So you are going to have what we call input layer. N1 is a variable, let's say age, S10 is the number of income, so can be one problem like that. So that's just it.
It's okay. It's okay. Let's go forward.
Okay. So multi-layer perception. Because the feedforward neural network is the simplest supervised learning network. These two are supervised, right? So this one is unsupervised. So these two are predictive, right? This one is descriptive. So in feedforward neural network, the movement is only possible in forward direction. So it moves from input to the output through hidden nodes if there's any at all. So each neuron is simply a linear equation, just like linear regression as shown in the following equation. So you have this kind of equation. So this equation is called the transfer function in a neural network. It is particularly suitable for the discovery of complex nonlinear models. So these guys apply them to give a particular output. We have the radial basis function network, which is also a supervised learning network. Works with only one hidden layer. So let's take note of these two. It might come out in your qualification exam. It works with only one hidden layer. And when calculating the value of each unit in the hidden layer for an observation, it uses the distance in space between this observation. And there's something. Okay, let's move on. So unlike the ways of multi-layer perception, the centers of the hidden layer of the RBF network are not adjusted at each iteration. In multi-perception, the weights are being adjusted to optimize the output. So you do adjusted weight and stuff like that to optimize the output. So the response of the units to an individual xi, the decreasing function g of the distance between the individual and its hypersphere. So as this function called the Gaussian function, it is used for the transfer function. The transfer function for radial basis function network is called the Gaussian function. While that of multi-layer perception uses what we call scalar product, like as it is here, it's just scalar product. But this one uses what they call Gaussian function. I think we should see what the Gaussian function looks like in the next slide. So the Gaussian function, okay, here we do look at the difference and the comparison. Here, for the hidden layers, the combination function is a scalar product. As you can see here, the scalar product, you have the scalar W0, W1, W2 to Wn. But in this case, you have Euclidean distance, as it is described here. Let me see. The response of the unit to an individual xi is the decreasing function g of the distance between the individual and the hypersphere. We use the Euclidean distance in this case. The transfer function for hidden layer is the logistic, while for the radial basis function, you use the Gaussian function. Number of hidden layers can be greater or equal to 1, but for radial basis function, it is exactly 1. For the output layer, we use combination function. But combination function, what is combination function we use for the output layer? Scalar product. But for the radial basis, you have linear combination of Gaussians. The transfer function is logistic. For RBF, you have a linear function. Okay. Speed, faster in model application mode. This one is faster in model learning mode. So why this one is not faster in model learning is that because it's adjust the weight. It adjusts the weight to optimize output. If you see the previous slide here, it's here. So unlike the weight of a multi-layer perceptron, the centers of the layer of the RBF networks are not adjusted at its iteration during learning. So that's why this one is faster in model learning mode. So what's the advantages of multi-layer perceptron is better generalization. For RBF, you have less risk of non-optimal convergence. Okay, so you can just take note of this. Now, the Cohort network is the most widely used unsupervised learning network, and it's also called self-adaptive or self-organizing network because it self-organizes input data. So in this case, the data is unsupervised. It's usually used for like classification. So the purpose of network is to learn the structure of the data so that it can distinguish clusters in them. Let's see. Which are the following statements is true about RBF neural network model? An RBF network is a supervised learning network. Is a unsupervised learning network, does not contain hidden layer. RBF network forms clusters of units at the output. So which one is correct?
RBF, the supervised learning network. I'm sure they made a mistake there.
Yeah, it's supervised. It's not.
Sorry?
It's not supervised. Yeah, I got that. So this, the option is not correct. Supervised not supervised. So, in which of the following kind of neural network, hidden layers can be more than one? I think we know the answer already.
I don't know the answer. I have to go back to the materials. That's what I think. But if they say MLP, then I'll now check to see if they are right.
So it is MLP. If you see the table, yeah, number of hidden layers greater or equals to 1. But RBF can only be 1. So we have learning rules. We have different types of learning rules. You have the opinion, perception, the delta learning rule, correlation learning rule, and house style learning rule. So let's see how far we can go with each of them. So the opinion learning rule is used to identify how to modify the rules of nodes of the network. So this learning rule states that if two nodes are activated simultaneously in the given network, the weight between the nodes is increased. So if two nodes are activated, the weight between the nodes is decreased. So if inputs of both the nodes are either positive or negative, a strong positive weight exists between the nodes. But if the input of the node is positive and negative for order, a strong negative weight exists between the nodes. So the Abelian learning rule is an example of unsupervised learning. So the learning is applied by equating all weights to 0. I'm not really feeling it. To 0. So the equation in the value of weights is proportional to the learning time of the network or the number of iterations. So mathematically, we have this guy. The weight ID is the unit I times the unit J. That's why you have it here that if inputs of both nodes are either positive, sorry, from this case, so where is it? If input of both the nodes are either positive or negative, a strong positive weight exists. So we have node xi and xj. If they are both positive, positive and positive is positive. If they are both negative, negative and negative is positive. So that's why you have a strong positive. But if they have different signs, then you have a negative weight. We have the perceptual learning rule, which is each connection in a neural network has an association with which changes in the course of learning. So according to this learning rule, is an example of supervised learning rule. It's the network starts its learning by assigning a random value to each weight. So the output value is calculated on the basis of the set of records for which the expected output value is known. So just like okay, let me try. I don't know how to put it. Just like you are doing a regression, you are building a linear regression model. You understand? So you know why is so let me use an illustration. You have let's say so you have let's say y is equals to this is a linear regression model a plus bx, for example. Now you used to have your training set, your test set, for example. Now let's say for this is a test set. You have your x value and your y value. Let's say so it's 23. This one is 24, 25. This one you have it 102, 105, 200. Now for my when I built my model now, This is my test set. You know, normally regression is the way you can calculate your A and B. But let's say I give it a random value. So I say my y is let's say 2.3. Give the random value 2.3 plus 4.5x. Okay. You know your y is already known. You have your x. You use your x to predict your y. Now if you put x equals to 23 here, and I get the value of y to be 110. Now 110 is the, so let me call it, I don't know, I want to try and relate to that guy. So this is the observed, let me call the, okay, this is the expected. This is the output that I got from this testing. Now I'm going to measure the error between the expected and the output. What's going to be the error? This guy minus this guy. So in this case, in this scenario here, we are using E minus I squared. So I'll use the expected minus the output. Then I'll keep giving this guy a random value till I find the one with a minimum error. So I find a value that is close to, like, let's say if I have like something like 103, then I can choose this. I'm going to choose this over this guy. So that's just the basis. So an example, so the network starts its learning by assigning a random value to each weight. So the random value is calculated on the basis of a set of records for which the expected output value is known, which is the learning sample. So the network compares the calculated output value with the expected value and calculates an error function, which is this guy, which can be the sum of squares of the errors occurring for each obtained as follows. So the network can adjust the weight of the different units, checking each time to see if the error function has increased or decreased. We have also the delta learning rule. The delta learning rule or Windrow learning rule is based on supervised learning. So the rule states that the modification is symptomatic weight of a node is equal to the modification of error and the input. Mathematically it's given as that. So we have here, this is the error function times the input layer. So this T, let's say this T is the expected weight, then this Y is the observed weight. So the static weight is now the learning rate times the error in the weight, which is like the expected weight minus the observed weight times the input there. So the real learning can be used with both single output units and several output units. So the aim of applying the delta rule is to minimize the difference between the actual and the expected output. That is the error, which is this guy, T minus Y right here. Let's look at the correlation rule. It assumes a strong positive weight exists between the nodes with the same sign of input as compared to the Ebenian learning rule, right? A strong negative exists between the nodes with opposite sign of input. So the difference between correlation rule and Ebenian rule is that the side weight DJ is used for weight calculation in correlation rule in place of 0 in the Abelian rule. So mathematical correlation rule can be given as this. So in this case, we are using what we call the desired weight. But in Abelian rule, we are using the product of unit I and unit J. I think this is where you should be able to differentiate between Abelian and correlation learning rule. Since desired weight is assigned by users, the correlation learning rule is an example of supervised learning. This your N is called the learning rate. We have the outstar learning rates. So let's see. Outstar learning rates, learning rule is used when it's assumed that nodes or neurons in a network are arranged in a layer. It produces a desired response T, layer of N nodes. This type of learning is applied for all nodes in a particular layer. The weights for nodes are updated as a co-NN neural network. So you have mathematically to be this. So weight JK is given as learning rate times output K minus weight JK. If node J wins the competition, but 0 if node J loses the competition. Okay, so let's see. So consider the following data for a neural network. You have the learning rates, you have the output, actual output, you have the target output, which is T. This is the actual output. So the input X is 16. On applying a learning rule, the change in sympatric weight is calculated to 20.984 units. One of the bases of the calculation of the given information identify which of the following learning rules is used. The answer is the delta learning rule. Remember, what's the formula for the delta learning rule? If you guys are following, you should remember that it is what? You can tell me.
That should be the what do you call this now? Changing the sympatric weight for the changing weight for let me know for high input.
You have an N, Abby.
You have the N, and that's the learning rate.
Times.
No, there's C minus Y now in brackets.
Yes.
That's the target minus the actual output times the what do you call that thing now?
The XI.
Yes, please. That's times XI.
So you have the learning rate to be given to be 0.1. This is 0.1 I saw now.
0.61.
Okay. Times the target is 13.21. 13.21. Then minus our actual input is 11.06. And I'll say the input X, then blah blah blah, which is what 16. Then I said what I said, on applying the learning rule of the blah blah blah, change in X, which is sympatric weight, is calculated to be 20.984. On this basis, identify which following rules learning rule is used to calculate the sympatric weight. So if you do our calculation there, if you are able to get 20.984, you can say that the learning rate that was used is what the delta learning rule. So let's use calculators to do this. Then we're going to get calculator. Let's use 0.6. So let me first do 13.21 minus 11.06. Have you? Is equal to this times 0.61. This goes to this times 16. 20.984. So that means it is actually the delta learning rate. I think that's cool. So let me see. Is Temitayo back with us? I don't think so. Dr. Magnus, are you there?
I'm here with you. It's just that I was thinking that the way you wrote that 16 is not over 16, but you are saying times 16.
It's time. Oh, times this 1 and 6.
Oh, it's 16. Oh, okay. I was looking at this. I thought it was divided by 6. Okay, now I got it. It's okay.
Dr. Abel, what's the weight? What's the sympatric weight to calculate for Ebenian learning rule? What's the formula? To calculate the sympatric weight for Ebenian learning rule.
Is that not the formula that is on the screen now?
No, this one is for delta learning rule. This is the formula for delta learning rule. I'm talking about the Ebenian learning rule. This is delta.
Okay, this is for delta.
Yeah.
Okay.
For the Ebenian learning rule. So look at our sisters with the Ebenian learning rule. Sudan, can you assist us on that?
Not the same as the correlation learning rate. Correlation learning rate. I think it's the same thing. Yes.
No, it's not the same.
It's the same as the correlation learning rule.
The Ebenian learning rate is xi times xj.
No, sorry, come again.
The Ebenian learning rule is xi times xj. That's the unit I times unit j. But for correlation learning rate, you have the learning. You have learning for the correlation learning rule. You have the learning rate times xi.
Sorry, I'm confused.
Times d times dj. Let me show you. This is see the correlation learning. You can see. See that of Ebenian.
Which one?
This for
Which one is this one?
This
Okay.
This is
okay.
This is Ebenian xi times xj for the weight.
Okay.
While for correlation, the learning rate times x.
This is X.
Okay.
All right. So let's take note of that. What about this? Consider the following data for a neural network. The change in sympatric weight is given as this. The input x is this. The desired weight d is this. To calculate the learning rate, you have applied correlation learning rule, right? So which of the following values represent the correct learning rate for a neural network. Myself for 2 minutes. So I have to excuse myself for 2 minutes. So Susan, you can share your screen, right? Susan, can you share your screen?
Screen. What do you want me to share? What do you want me to share?
So we want to solve this problem. I said, which of the following values represent the correct learning rates for the neural network? You are given this information. You just need the learning rate. This is like the end signal. You need to find this end. So how do you find n given this information? Notice that you are using the correlation. You are using the correlation learning rate. So I'm waiting for Susan to share her screen so I can answer.
What do you want me to do? There's nothing showing on my screen. It's your screen that is showing on my own. I'm not seeing anything on my screen.
You cannot share. I said you share your
I'm
screen.
not doing anything there. Do you understand?
Okay, no problem.
What do
Okay,
you
let
want
me
me to
just.
share?
Okay, don't worry. So I'll just okay. You just tell me what to do.
Okay, how to calculate this stuff.
Yes.
Okay. And since we have that one, we are going to use the formula now.
Okay.
It's going to be 19.9 equals to n times 16.79 times 26.88.
Okay, let me go back to my drawing board. That would be 19. You said 19.9. I use okay. Let's go back. 19.8, Abby.
Yes.
19.8 is equals to
Equal to n x is 16.79.
equals to 15.79. Okay.
You didn't put the n in front of.
Okay. Okay. There's supposed to be n in front. Okay. This is the n, Abby.
Yes. Times
Okay.
now. I believe there's times there.
And let me help you. 19.8 is equals to learning rate times 16.79. Abby, is this 16.79?
And 16.79.
Yes. 79,
Okay. Times Abby, is it times again?
Yes.
Times, not times. It's times.
Times
Times 26.88.
26.88. Okay. So what do we go for? Where do we go from here? What do we do first?
Anyhow you want to, I think I do it in 2 ways. You can say 19.8 equals to the multiplication of all this one.
So how do you find n from this formula?
What we get from this one, we'll divide it with that.
So just tell me what to write.
So 19.8.
19.8
Equal to,
is equal to
yes. That should be 451.31315. Let's do it to decimal places. 451.
451.
0.32.
0.32. So how did you get this 451.32?
This is
3.7.
9.
Sorry?
16.79 times
16.79, yes.
26.8.
Okay, that not give us this one.
You now have
3.88.
n. You have n and that number. I don't have a calculator here.
It's 16.88. I'll be 26.88.
Okay, 26.88.
Just
Okay.
tell you one decimal place.
So how do we get 451.32?
16.79 times 26.88. You get 451.315. But I approximated that one to be 2.
Okay, so what would I write next?
N now.
The n.
Okay, N. Okay.
N in
Then,
front.
so what should I write again? N like this.
For you to look for what the N is, you divide that one.
Okay. What should I divide? This I'll divide
It's
this one.
19.8. 19.8 divided by
451.
451.
451.32. Abi? Then this one to be 451.32. Is that what you are saying? So this one will divide this one. Then Abi, N is equals to 19.88. So that's 19.8.
Value is going to be small.
451.32. Okay. That's 0.0.
Zero or something.
Is it 43 I'm saying there?
0.04.
4387, so something like that.
Mm-hmm.
Okay, let's see.
That's the option.
Answer examination. Okay, no problem. So moving on. You have algorithms for training neural network. You have the gradients, we have the descent, evolutionary algorithms, genetic algorithms. Then we talk about let's see what comes to about them. So gradient descent. The algorithm is used to find the local minimum of the function. These algorithms convert the local minimum. Sorry, let me meet Dr. Adem. I think my voice is echoing from his end today. All right. Convert it to the local minimum by pushing proportional to the negative of the gradient of the function. So what's more conversely to find the local maxima, the steps are taken proportional to the positive. So what's even local minimum? What is local maximum? So let's say the function has this curve of a thing, as you can see in this picture. Now, if this is the starting point, now it goes like this, it goes like this, it goes like this, like this, like this. Now, at this point A, we have what we call local minimum. At this point A, we have what we call local minimum. So why is it called a local minimum? 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 Why is it called a local minim because at this point A, you have the first minimum value. So you can say it's starting from this point, but you are not considering it's still starting from. At this point A, you have the local minimum. But if I consider point A, point B, point C, this is actually the minimum. But at first, it was observed at A. At first, so that's why it's called local minimum. At first, we have the minimum at point A. Then, before we now talk about global, so this one is called the. So if you compare A and C, C is called global minimum, where A is called local minimum. Then you can have what we call local maxima and global maxima. Stuff like that. So this is a global maxima. This is a global maxima. That's a local maxima. So unlike linear models, neural networks are complex non-linear models where the error surface has an irregular length. To define the minimum point of this surface for which no maps are available, the user must explore it. So the gradient descent algorithm moves over the error surface by following a line with the greatest slope. As you can see here. So as the figure shows local and global minima. A is the local minima and C is the global minima in this case.
Hello, Iman. Hello. I say A is the local minima.
Yes, yes.
Which means the global minima will always be the last. Or I was thinking it should be the deepest point like B.
So the thing is, when you talk about local and global, so if I consider these 3 points, for example, I consider these 3 points. Now, these are just considering these 3 points. Now, which one is, first of all, which one is coming first? A. A is coming first. At this point, you can say you have a local minimum because it's the one that starts. You first of all experience this guy before you go to space. Now, this person is bigger than this person, so I cannot call. So out of these 3 points, this one is the smallest. So that's why I call it the global minimum. Now, if you compare these 3 points too, you see that this first, we first of all reach this point before we reach this point. At this point, you have the local maxima. But at this point, you have what we call the global maxima because this is the greatest of all of them. So let me show. Let's illustrate more. That's local minimum maximum. So, okay, let's say local and global maximum. So let's explore this. Which one should we use? Let me see this graph. If you look at this graph now, we have local maximum here, and you have global maximum here. So you usually consider the edges. So this guy, you have local maximum because this is first guy that's like the maximum, the first maximum you experience here. Now, this is the biggest of them all. Let's go to global. Now, let's go to what we call local and global minimum. I think this one is the global minimum because the smallest of them all. But I don't. Okay, so okay, let me explain the points now. The point is that first of all, identify the global maximum, the global maximum. Then the points before you get to the global maximum is called the local maximum. Now, after you identify the global minimum, the points before you experience the global minimum is called the local minimum. So let me use another graph again. So if you look at this guy, global maximum. Now the points that follows this guy is this point. Like after the maximum, then you have this guy, this is called the local maximum. Now this one is the smallest of them all. But the point that follows is this guy, so it's called the local minimum. I think that is understood by now. Or do I have to explain further? Or let me just use a simple set. So let me use a simple set to explain this so that we can get it. So if I have a set 1 to 5, for example, if I have a set 1 to 5, 5 is the biggest, highest of them all. So 5 in that case is the global maxima. Then 4 is one that follows. So you call that one, you call it local maxima. So out of 1 to 5, the one that is smallest is 1, so you call it global minima. And the one that follows, like the second smallest, is 2, so you call it the local minima. I think that part is clear. I have evolutionary algorithms, which is based on the concept of natural selection or survival of the fittest in biology. Can read more on that. And I think under it we have so 2 basic elements of evolutionary algorithm and variation operators, which consists of recombination and mutation. Selection process is selection of the fittest. What are the common features of evolutionary algorithms? It's population-based, uses recombination mix candidates of the population and creates new candidates. Also based on random selections. Some common evolutionary algorithms have genetic algorithm, genetic programming, evolutionary programming, evolution strategy, neural evolution. Neural evolution algorithm is used to train neural networks. The genomes are used to develop neural networks by specifying structure and connection with. Okay, so you just have to read more on that. Okay, which of the following kind of evolutionary algorithms the genomes are used to develop neural networks by specifying structure and connection with neural evolution? As we can see here, develop neural networks by specifying structure and common connection with. Okay, so I think let's look at this too. Converging to a local solution is a common problem in using gradient descent algorithm. So, why using this algorithm with high learning rates, which are the following strategies, will help you to avoid the convergence of the network to a local optimal solution. I think we need to read more on this. But they told us using the learning rates, probably when we read more on this, we understand that. So, I think that would be. You have to specify this one. Okay, let's look at this. Implementation of neural network in lab. So to implement this neural network, let's consider the scenario of a reputed real estate marketing company that wants to predict the customer response while purchasing land. So we have a set of training data that contains information about the customer and a set of testing data from the customer that wants to predict. And we want to predict that way. So the company needs to analyze customer response using the machine learning algorithms with training data sets, you are using neural network as a supervised learning algorithm. Since you are predicting the supervised learning algorithm, to predicting when it's a predictive model, you are using neural network as a predictive model when it's supervised. But when you're using it for descriptive purposes, it's unsupervised. So to predict and analyze data and provide relevant information. It's doing me as if I should write my exam today. So. That's how it's actually doing me now. Suzanne, are you there? Suzanne, is Suzanne on the call?
I'm listening.
I
I'm
said,
here. I'm still here.
I feel like writing exam today too.
Can you hear me?
I can hear you.
Yes, I'm still here. I'm listening.
I said, do you feel like writing exam today too?
Do you do what?
Do you feel like writing exam today too?
No, at all. I'm not fully prepared.
So by integrating data sets into a neural network algorithm, the company can predict customers' response. So we have the list of variables used in this data set. We have the response, which includes two values, 0 for no response and 1 for response. So we have the spend ratio in the data, which specify the amount of money a customer can spend. So it's just like if I go to market, okay, I have the intention of buying a wristwatch. In your mind, you already know that though you don't know the watch you want to go and buy. You shall know that I want to go and buy a watch. But in your mind, you already know if the watch is above 5,000, me I cannot buy it. So you already know that you cannot spend above a particular amount, even though you might like the watch so much, but you cannot exceed a particular amount. So to this specify the amount of the money does not spend. Age 1, specify the age of the customer. Debt ratio, specify the financial ratio. As the ratio of the total debt to total assets of the customer. Monthly income, specify monthly income of the customer. Entry index, the education level of the customer. Own houses contains an integer value that is the number of houses a customer owns. So we are using the steps below. So import the training and testing data. Import and load the neural nets and DNWR packages. Load the training data, load the testing data, build a neural network for the given data, load the graph of the neural network, use the compute function to get getting predictions for the test data, and get the final prediction in a CSV format for our API. Really like anyways. So you have developed a neural network model for given data sets. Now, which of the following commands will you use to make predictions for the generated neural network model? Is it plot? Is it compute? Is it library? Is it write? The answer should be compute now. The answer should be compute. If you look at use the compute function to generate predictions for the data set. Using plot the graph of the neural network. How does it? So to generate the predictions, you use compute. So next, and this is just a summary. So let's go to our lab environment and see what we can do. So okay. So we have two labs I want to do. So let me just first of all, delete this guy. Delete this guy. Then enlarge my screen and go to my lab manual. In this case, we want to, I think it's on desktop. Graphical. Okay, graphical models. That's the best one to do. So I'll copy this and paste it here. Analyze a large amount of data using graphical models in R. So we start the lab by creating an empty DAG. So who can tell me what DAG means?
I didn't get an idea. What?
DAG.
What DAG means?
The topic there.
Let's open my book.
So DAG means directed acyclic graph. Directed acyclic graph. So let me just like, I think, did you get it?
Yeah, directed acyclic graph.
Acyclic. So acyclic graph. Yeah. So that is DAG. So install due package. We are going to install due package. I think I already have that installed. Then import the library. So I'll just use this guy to load the library onto it. So call the data. So the KSL data is comes with the package, the due package. Then I'll just load it. So 1 minute, please. Oh. Good one. Okay. So then I use the network. That. So I want this. Control enter. Sorry. to enter. So it has been stored in this. So let me just call it and see what's inside. So this is what is inside. So you have this these columns. You have 9 columns there. So let me see whether we have a description in the
Emmanuel.
Yes.
Sorry, I missed some parts.
Okay. So first of all, we load the.
Dr. Abel has even left.
Maybe
His
it's
network went off. Yeah. Because mine too went off some minutes ago.
I think I noticed that too. So let's even see what's inside the case editor. So you have this data. These are the columns that are there. So we just created an empty tag using the network function on the data sets. Then this is what we have in the empty tag. This is what we have. Then what we are going to do here now is create. This is going to create a joint probability distribution for the data sets. This guy we have created here. So joint distribution of the discrete variables. So if I should run this now, let me see. Let's see what's inside. So TSL dot graph. This thing is very long, so let's see. This creates a joint probability distribution, as you can see here. But if you see in this result here, let me see. 12.5 BMI. Log BMI on the left of that. So this creates the joint probability distribution. I don't think we really need this guy. This is supposed to be used by creating a band list. I don't know why they created this guy anyways. I don't think it's necessarily needed. Okay. So to build the model, first of all, this guy, if I should want this guy, is going to assign parameters to a tree. So I'm going to have a tree. It's going to using the learn function. So let's see what the learn function does. So learn. So the learn function, I'm going to have inside NWDL. So out of all of these things I need, I just need this guy. So first of all, let me run this guy without calling this guy. So let me run this. I'll copy this guy. Let me put it here. So okay. So let me call it ksl.new. I have all of this information here. But I just need this part. I just need this part. So that's why we're putting this ampersand new here. I can just write it and say ampersand is equals to ksl.new ampersand NW. So I've done that, so I don't need to run this one again. So this is going to evaluate the dependencies, since that's what we want to do. So we are going to use the heuristic function to do that. So you give, so let's see what the heuristic function takes as a parameter. The heuristics. You see, it takes this guy that we have computed as the first parameter, which we want to specify there. Then takes the original data, which is the KSL data. Then the joint probability distribution. Now the restart, the restart they have here is 10. They are using 2 here. I think this is the number of iterations that is used when building the model. But I think by default it is 10 here, but it's 2 in there. I can put 10 here. But this degree is usually the size. So let me to the heuristic function. We check this guy again. Your degree is supposed to be the size of your first parameter, which is this guy, and it's supposed to be 9. So let's see size of KSL dot z.nw. Yes, it's actually 9. So I don't know why they put 10 here anyways, but I'll just put degree equals to size, which is the number of variables you are considering here. KSL dot NW. And taking trace equals to true, which means it's going to plot a graph for each iterations. So doesn't matter anyway. So let me do this. You can see what it is doing at this right hand side. Did you see that? Hello? Hello?
Hi, Manu. Yeah.
Did you see what happened at the right hand side here? At the plot section, where we have the plot. Yeah. So I didn't get that. What are you saying?
Which one? And this one?
Yes, this plot we're having here. Did you see what happened as we were talking?
Yes.
So putting trace equals to true here means it's going to do a plot for every iterations. So I'm going to have a plot for every iteration here. But if I shouldn't put this trace equals to true here, then you might not see this guy here at this. So I will just put. So I'll call obtain the best fit of the graph. It's just like you are obtaining the cocoa of all you need from the result model, which is the NW for the result. So let me see. Again. So I will just change the end of it. So let me run this guy. So I didn't like the way this guy is plotted here.
Which one? This one is clustered together.
It's just annoying. So let me use Windows function. If I use Windows function, it's going to. So let's say 9,8. This is going to create a frame where you can have the plot. So this frame, can I see this frame at the right hand corner?
I can. Yes.
Yeah, you said?
Yes. Yes, I can see.
So but you plot now, it's going to appear on this frame rather than on this lower part here. So let me run the result again. Let me show you the frame. So you can see as it's showing here. So it's more
Okay.
it's more clearer than what we have here. So if you check your manual, your lab manual, what you have here, this is not the best fit anyways. This is not the best fit, but these are our final results here. So it means from here you are saying that sex, alcohol with, let's say this alcohol with, is dependent on year and sex, whereby smoke is dependent on year and sex also. Work is dependent on year and sex. Smoke is dependent on sex and alcohol. And I don't know what am I saying? Smoke is dependent on year and sex. FEV, I don't know what FEV is, dependent on smoke, sex, and year. Like dependency. So this parent, this a parent, this is a child. So you can see the dependency, the plot of dependency on each of these variables with this graph. So this is an example of a directed acyclic graph. So that is by the way. So let me see this guy. Also that I can do a plot based on different one. There's no way I can do this guy. What's the name? Let me see. Best fit. So we have seen the how that actually works in graphical model. So let's see the neural network illustration. So I'll close this. Then I'll choose one to open. Okay, so so first of all, I think I have this libraries that these packages installed already. So what's the background of this lab? Reputed Real Estate is a property management company promoting a new residential project. The company has a large amount of data stored in data sets that contain customer records and their response to the previous RRE projects. So the IR management of RRE wants to analyze data in order to predict the success of company's new project. So the owner found out that the most suitable technique for analyzing data of the company as is the machine learning algorithm. So one of the most common used algorithms is the neural network, which is power scaling algorithm. The neural network analyzes input data and provide a precise optimal result. By integrating the training and testing data sets into the neural network algorithm, you can predict the response of customers for buying a real estate project. So we are going to help our to analyze the behavior of customers and predicting their responses to new projects. So first of all, we log into. I'll just load these packages. So let me load this. I think I should have it here. Okay, it is loaded. Let me load this one. Okay, so I think we have a training data set, but here I'm using my local PC, so the the location of my data is different from this guy. So first of all, let me get working directory so that I'll just copy. My direction is desktop anyways. And my data set is under desktop. So paste here. Then I have to put desktop here. Slash. So I've loaded the data, the training data. So let me see. I call it training. So testing. So testing. So let me just copy this again and put it here. So I'll put my testing data too. So let me see whether I can view my training and testing data. So this is my training data. We have response, spend ratio, age. So let me see. Response, it stores the response of customers. The value of the field is set to 0 for a customer who does not give a response, and 1 for a customer who gives a response. Spend ratio stores the amount of money a customer can spend to make a purchase. Age is the age of the customer. Debt ratio, monthly income, with own houses. I think we talked about this in the slides. So let's go back to our work. So we've loaded the data sets. What next do we do? So here, what are we going to do now? What are we trying to do? So now enter the following commands to load the testing data set and perform the inputting and scaling operations on it. Here we are doing imputation and the training data sets. Then here we want to scale. First of all, let's do this. Where's the view of our training? These are our training data sets. First of all, then let's see what this is going to have effect on it. Let's see what the training data set looks like. Look at this guy now and this guy. This is training this. So there's not much difference in it, but it is just for you to work with this neural network of it. That's how you have to do that. So the training data set itself, we want to combine the first column, which is what the response data, which is what we want to predict, comma, scale. So we want to scale every other variables. So from the second, third, fourth, fifth, sixth to the 7th column. So we want to scale the second to the 7th column. So scaling means we want to make the values between, it can be -1 to 1 or 0 to 1. So I want to normalize the horizontal. So that for it to, just to improve the efficiency, the processing of the model. So I should run this. So let's look at our T data looks like now. Our T data, okay. So look at the T data now. It's quite different from what our chain data is. So look at the age. You have 248, blah blah blah. But look at the age. it's being normalized now. So it's being normalized. So it's between from minus something to something. So we want to give our T data a name. You know it is column binded. So it means it's not going to have a name. So if we see this, okay, let me even go to this. Look at V1. V1 is supposed to be the response column, but the column name is called V1 because of the way we put it here. We call save and chain into square bracket, comma 1. This one is not going to generate, didn't generate the column name for us. But here we want to give the column name. So column name of the T data is going to be. So we explicitly gave the first column to be response because that's the column name originally. Then for others, just generate the column names from the T data itself because it didn't change. Their column is still the same thing. So just give us the column names for the T data itself combined with response. So it's going to change the column name, the header. So if I load T data, if I click on T data again, you see that the column name has changed. This one has become response. So as you can see. So let's do centralization on test data also. So let's look at our test data. Let's look at our test data. Look at our test data. It just has those column, except from what? The response. Except from the response. Doesn't have the response. How many column? They have 999 results here. Let's see our T data. How many of them? So you have so many of them. So you are using that one to test. So let's go back to our. Have I scaled? I don't think I've scaled. Okay. So let's scale our test data also. So let's build our neural network model using the neural net function. Since we are predicting, so I'm going to model the response based on other variables. So we are building we want to build a model predicting the response based on spending ratio, age, debt ratio, monthly income, edu index, owns houses. Now, you know, you didn't call the columns based on the data. So you have to specify, okay, which data are we referring to? So that's why you have data is equals to T data. So you are using the training data set to first of all build our model. Hidden equals to 1. So just have one hidden layer, then error function. What's SSE? What SSE here? So let me take a look at our neural net function. Neural net. Okay. You have I think this is it. The formula, the data, hidden equals to 1, your hidden layer threshold. Is there, okay. The error dot FCT, the error function SSE. Okay, what do you have again? Linear output. Here you have to be false. It's not linear output. Threshold. Our threshold here is we are taking the default value 0.01. Okay. So let's run this. Okay, I think we have built the model successfully. So let's plot the neural network. So these are our neural networks. Like hidden layer. So these are the input layer. Then you have hidden layer because we specified hidden to be 1, right? Then these are outputs here, as you can see here. So here, predictions. You want to combine the testing data. Is it testing? Let's testing. Okay. So let's even see the testing that we imported. Let's see what's inside. Okay, it has 6 variables. Okay, the response variable is not there. I don't know why we are not using the wait. I don't know why we are not using the scaled test data. Why we are using the original. Okay, so testing. So we want to provide testing data set and compute using the compute function to predict. So you are compute using the model you have already built. Then so let me see the compute function again. Compute. So compute X, then covariate, then I think maybe number of repetitions. That one might not be necessary. So covariate with the data set you want to use to make the predictions, which is the test data. You are considering everything in the test data, not ignoring any column at all. And we just need the net.result out of this particular output. So it's going to predict this guy, but we just need the output, which is stored in the net.result column. So we want to compile it to this guy. So combine it together so that we have the response just beside it. Do you understand? I think I will even prefer the output to be first, then the other columns to be second, or any which way. So so let me run that. Okay, I want to give it a name. Column names of predictions will be combined column names of predictions, excluding the 7th column. You know, the 7th column is the predicted value here. Then, so I'm giving the predicted value a name called net.result. So you know that that's our predicted value. So let me run it. So let's see our predictions that we made. So this is the predictions. You can see it has 7 variables. So the 7th variable is the response that we predicted. So this is the result we have. So it means that this guy predicted that, okay, based on this information, this person is not likely to buy. You can see it's 0.00000. But let's see. Let's proceed downward. Wow. Okay, wait, I saw something now. I think I'm too fast. I think I've passed this thing. Let me go over it again. So, okay, you can see this one is very closely to 1. which is okay. Then this one. Then this. So you can see all those values are very close to 1. So each gives this prediction. So that's how you predict using the model using the neural network. So you can save the output as a CSV file. This write.csv command as it is. So if I want to save on maybe on desktop, let me just try to say this. So I'll just copy this guy. Let me copy this guy now, for example. So I think this is how it's saved for us to as a CSV file. So let me run. Let me check my desktop folder if I have the results there. What's the name of the file again? And the predictions.csv. Predictions.csv. As you can see here, predictions modified 5th of September 2021. So if I open it, so you can see my results as a CSV file as you are seeing it here. So this is it. So that's beautiful. So that will be all for today. So next week we're going to talk about dimensionality reduction, support vector machine. We should be able to cover to finish machine learning next week. But just please. Maybe we should be able to cover. There's much more. So next week we should be able to cover machine learning by God's grace. So is there any questions so far? Hello.
Hello, Emma.
Sir.
What I see in these programs is not something that you just do once. Thank God the programs are already in the system, so it's a question of learning them and understanding the procedure, because now the program was written by somebody. You have to understand what is done and then how to do a manipulation. For you, you have been doing it, and so it's easier for you to manipulate. But for you adults like us, it's not going to be as fast as you are thinking. So gradually we'll go with you. So, but I'm not strange to programs, because most times I work with programs already. I'm not strange to programs. I know what it means for what you are doing. But if, like, say, you're asking now, I'll say, okay, because I've seen the manipulations you've been doing. It's a question of what do you want, and make the necessary adjustment to fit in to what you want. I think it's okay for now. If I have challenges, of course, be sure that I will call you.
Definitely.
No problem.
Susan is the one you should understand. They are younger and they are smarter, and she must have been working with this.
No.
So
I'm working with Araga.
my head is full of so many things. So it takes time to delete some and to upload some.
Upload some.
It is well. But it's interesting. It's interesting. I am at home with most of what